Cool. So once again, hello to each of you guys, and I hope that you're all doing great. In the previous session, I just did my best to get you familiar with the systems, VU Collaborate, how to log in to your VU Collaborate. Also, I'll show you how to get access to the content, how to get access to the assignments template later on if you wish to upload your assignments, how to do that. Also, I'll show you how to get access to your unit guide. Unit guide provides you with more information about the unit, and also you can see the due dates for each assessment task. In this first session, I would like to just go to the very basic of computers, talking a little bit about binary, talking a little bit about hardware and software in a computer, and slowly to get familiar with programming language. And then we go and start using Python probably in the next session or maybe next week. In the first session, as I said, I'm just going to the very basic things. That's the agenda for this first session. First of all, I just want to do the acknowledgement of country. So we acknowledge the ancestors, elders, and families of Kulin Nation, who are the traditional owners of university land. We also acknowledge all traditional owners of country throughout Victoria and pay our respects to their culture and to their elders, past, present, and future. As we share our own knowledge practices within the university, may we pay respect to the deep knowledge embedded within the Aboriginal community and their ownership of country. We also acknowledge that the land on which we meet is a place of age-old ceremonies of celebration, initiation, and renewal, and that the Kulin people's living culture has a unique role in the life of this region. As I showed you in the previous session, you have a couple of options in your Zoom, so you can raise your hand, and also you have two options if you want to send a message. You can send it to the whole group, so all of your classmates are able to see that, or you can send it directly to me if you want to send me a private chat. You can do that. Also, there are a couple of icons in the previous session. You just played with that. If you want to raise your hand or if you want to ask a questions, obviously you're free to do that as well. I don't want to be the sole trader in the class, and slowly I will ask you guys also to contribute if you wish, and also if you have anything interested to the class. In all of my sessions, I have students being in IT for ages, and definitely they can help us to improve the class experience. As discussed in the previous session, I assume that all of our classmates have no IT background. And considering that in my mind, I will do my best to deliver a first-hand, engaging, and practical delivery to you guys. Let's to move on. Learning outcomes for this unit is designed for aspiring IT professionals, and we will learn about the language, data types, operators, expressions and variables, basic language, syntax, what is an error, what is debugging process, and all of those things. If you remember in the previous session, I show you our assignments, and the assessment task one was a short answer question. But in the assessment task two, we had something like a project creating code to create a password manager. And there have been a couple of terminologies that probably you faced and you see them in the first time, like syntax, debugging, and all of those things. It's the content of our first few sessions. Sequence, selections, and iteration, creating functions, loops, and all of those things we will discuss in this unit. The development of a small size applications, I will ask you in the next few sessions with so many practical activities. For example, on how to write the code to create a converter, how to write a code to create a menu, how to write a code, all of those things. It's good to mention that by doing this unit, we don't want to be a programmer, and we cannot obviously as well. We have just a few sessions just to get familiar with the very basic principles of programming. If you ask why this unit might be important for certificate 3, or after that we will have another one which is coming from certificate 4, why it's important to be familiar with the basic of programming. There are so many different reasons. As I use an example in the previous session, probably all of us, we do driving. You may have a car and you do driving. Does it mean that we are all experts in car engine? Does it mean that we are all mechanics? The answer is no. We know how to use the car, but we are not expert in, for example, making or building a car. That's the same things here. We don't want to be programmer by just doing this unit or the other unit after this. We want to know how it works. We want to know how the logic is working. Because later on, if you go to certificate 4, we will have so many units that we need to know how to write some basic codes or how to interpret it. For example, in certificate 4, we will have so many units talking about automation. Imagine, for example, in a big campus, in a university, in a hospital, in a factory, there might be hundreds of PCs. Is it possible, if you want to check all the PCs meets the minimum security guidelines, is it possible to do it one by one? Imagine in a university, there might be 4, 5, 10 campuses. Imagine in a bank, for example, ANZ Bank or Commonwealth Bank, they have hundreds of branches. In each branch, there are hundreds of devices like servers, PCs, workstations, mobile devices, IoTs, and etc. If you want to check if they all have the latest operating system software, if you want to see if we have the minimum security baseline, is it possible to do it individually, one by one? It's possible, but it takes ages. It takes too much time. So obviously for that type of works and tasks, we need to use automation. And we will see how we are able to, just using a couple of lines of code, perform a task which may take too much time for the human to perform it. Scanning a network. Later on, we will get familiar with networks, different devices in the network, and what is an IP. Imagine that we want to scan a wide range of IP numbers. By using these scripts, we can simply use a couple of lines of code and scan a big, massive network in just a few minutes. There are so many advantages using this programming language in networking, in the cloud, even in the cloud units. Later on, we will have a cloud unit and we get familiar with AWS, Amazon Web Service, and we get familiar with Microsoft Azure environment as well. And we see how we are able to use scripts instead of just, for example, clicking here and there to, for example, start a web server in the cloud. We can use scripts by writing some codes. We are able to start servers, to stop them, to increase the number of web servers, all of those things. It's possible to do it in PowerShell, or it's possible to write some codes in Python using so many available libraries in Python, and performs all of those tasks in a very, very short time. So in this unit, we will work with functions, loops, iterations as well. And also we get more idea about the debugging process. Nowadays, because heaps of these platforms that we use for Python programming, they equipped with AI, it's much easier to find errors. But previously, it might took so much time. When I started working with Python like 14, 15 years ago, when we had an error in our program, sometimes it took us like 8 hours, 9 hours to go and find where that error is coming from. But now heaps of IDEs, they equipped with debugging features. It means that they can give you a quick insight where the error is coming from. I will give you more information about the debugging process in today's session. Unfortunately, the PCs are not smart enough if we don't follow their rules, or it's better to say if we don't follow their syntax. Even having an extra dot or having an extra slash, it may cause a code with hundreds of thousands of lines of codes to stop working. For humans, it's not the same. For example, if you know a little bit about Chinese or Japanese, and you just go to Japan or China and start talking with the people. Obviously, we are not fluent in those language because we just learned those language pretty recently, but those people are able to quickly understand what do we mean. Doesn't matter if our pronunciations or if our grammar is not 100% correct, they are able to understand. But it's not the case for the PCs. Today, we'll talk about interpreter and compiler based programming language, and we get more information about debugging process. Testing should be the last steps in our writing the codes. We go and test it in different scenarios. We want to make sure that our code is working appropriately. The other things that I need to mention, also, if you want to be a penetration tester, usually in my classes, heaps of my students are so keen to know how they can be a penetration tester, working in ethical hacking. In that field also, we need to know so many things, and we need to be proficient in programming language. Again, as I said, we don't want to be a programmer just by doing this unit or the other unit after that. We just want to know how to use, how to interpret, and how is the logic of programming language. So that's the learning outcome of this unit. I will switch to my board. Usually I use board a lot in my classes, and I go through some basic things. As you see here, we have the timeline for this unit. and there are 12 sessions. As you see, end of the month is the last session that we have. And also, as discussed in the previous session, I do my best to wrap up everything in 9 or 8 sessions and keep the last 2 sessions as a buffer for those ones that might be still behind or they need extra assistance for their assignments. Usually in the last sessions, if all of your assignments are submitted and you got satisfactory results, as a bonus, I just ask my students they can go and enjoy their time, or if they wish to stay in the class, that's totally fine. But usually the last session, I'm available for assignments and assistance, extra assistance if anyone needs. Let's to go down and start talking a little bit about our tonight's session. As you see again here, we have the assignments. I already talked about that. Let's to switch to my board and start talking about a PC, what is a software, what is a hardware, what is binary, and what is a programming language. So let me reshare my screen to my board. Okay. Unlike the traditional classes that usually teachers they have their older style boards in online classes, I use this digital board for writing something. And let me see if my screen has been shared. It seems that it's shared. Yes. Okay, cool. Okay, the first thing that I want to start talking about is talking about a PC. I know that we all know what is a computer, what is a PC, and you're familiar with all of those things. But for those ones that they might have the interest to know a little bit more about these things, let to firstly start talking about two main components in a PC. So when I'm talking about a PC, doesn't matter if it's a laptop or if it's a workstation with a case. Later on, if you proceed to certificate 4, we have a full unit talking about computers. And we go through all the main components like motherboards, talking about different size factors, talking about different types of CPUs, CPU families, talking about the frequency, clock rates, different types of storage, different types of RAMs, different types of graphic cards, and all of those things. We will have a full unit talking about hardware components. And also after that, we have another unit talking about software. And we go and learn more about Windows, different Windows families like Windows 10 and 11 and Windows Server family. Also, we get familiar with Linux families, different distributions of Linux like Kali Linux, Ubuntu, Mint, Fedora, Red Hat, all of those things should be in certificate 4. In this certificate 3, we just go to the very basic things. So when I'm talking about a PC, you can assume you have a laptop or you have a workstations in your home, and it has two main components, hardware and software. So when we are talking about hardware, obviously you know what they mean. Hardware is any component which is physical and you can see and you can touch it. It's a tangible component. For example, in your PC, in your laptop, if you open your laptop, if you open your workstation's PC, you see there are a couple of components like a fan, a motherboard, RAMs, so many different PCI Express slot cards, and all of those things that you can see and you can touch it. They are all hardwares. Your mouse, your keyboard, the monitor, they all are hardwares, physical components in your computer. If I want to give you an analogy, just like components in a body, like your hands, your foot, and all of those things. But what is a software? If I ask you, what is a software? A software is something like the brain in our body. So in order to move, in order to play, in order to do some actions, obviously the brain needs to send some commands to our body parts and then they are able to action, they are able to work. If I ask you, where is that software? If you open your PC, if you open your computer, are you able, for example, to see a software like Microsoft Office? Is it possible, for example, to open your phone and you see the iOS or Android if you're using an Android phone? The answer is a simple no. But what is those softwares? Those softwares are a bunch of instructions which tells the hardwares on how to perform, on how to operate. So we will focus more in this area today. For example, in hardware, in software, you may have so many different types of softwares like Microsoft Office, like, for example, a browser like Chrome or Firefox, Safari. It might be a game like Minecraft. They all are softwares. Today, I just want to focus a little bit more on this software to see how they work, how they operate, how they created, and in order to do that, we need to use binary. As discussed, the PCs just made by plastic and metals. Your laptop, your workstations, your PC, your phone, they all are made by plastic, or they may have a titanium or aluminum body, but they all made by copper or plastic and metals. So how to interact with those devices? If we have a laptop and it's raw, it's blank, it doesn't have any uh, operating system, software, etc., how we are able to communicate with this type of devices. I can see that you put something in the chat, and when I stop talking, I'll definitely go to whatever you put in the chat and I answer that. Firstly, I want to use a very simple example. Imagine that you have, let's say, a younger brother or sister, or if now you are parents and you have kids, imagine when you've been younger, imagine you have a younger sibling and you have an agreement between you and, let's just say, your younger brother or your younger sister. Imagine it's a Friday night and they tell you, yes, we are going out and we want to enjoy with our friends and we have a party. It may take till up midnight or even after that. And when I arrive home, I just want to make sure that if everything is okay, mom or dad, they are not waiting for me, they are not angry. So let me know if everything is okay. But imagine there is no way to communicate with a phone or there is no phone available. Imagine the only things that we have is a light. Your home light, let's say. So we agreed that when, for example, your younger brother or younger sister, when they arrive home, they can slowly knock the door. And if everything is fine, for example, the mom and dad are okay, they didn't notice that your younger siblings are not home. If everything is fine, you will turn on and off one time. So turn it off and turn it on. So when you do that, they know that everything is fine just by turning off the light one time and turn it on again. But imagine the situation is not okay. So again, we agree that, look, if I turn off the light and turn it on and again turn it off and turn it on for two times, so you know that you are in trouble. So be ready, have some excuses or some things because it's not okay for you to come in. So it's a pretty simple agreement. We did have all of these type of agreements or communications ages ago. For example, when boats and ships in the oceans, they wanted to communicate with each other, they use lights. For example, flashing lights or color lights, they all have a message. They all have a type of message. We also still use them in our traffic lights. In a traffic light, you know that when it's green, you can go. When it's red, you should stop. What about when it's orange? You should push the pedals on. So you see that still we are using this type of communication. Why this type of communication is used in the computer pieces? Because the computer, as discussed, it's made by metal and plastic. The only things that they can understand is electricity, or let's say voltage. They can understand voltage. Obviously, when you use, for example, a battery and it has 1.5 volts, you cannot feel any voltage. But for example, if you touch a 9-volt battery, probably you can feel a little bit, specifically if you touch it by your mouse, you feel the voltage. Or for 1.5 battery also, if you just touch it by your mouse, you can feel it. That's the same in a PC. They can feel, they can detect voltage. So that's awesome. That's all good that we can communicate with them using voltage. But the problem is how we are able to translate our own language, our numbers, alphabets, symbols, all of those things. How we are able to translate our own language to voltage and then just save it somewhere in a PC or a computer so they can understand that? The answer is just using this way of sending voltage. In this case, when I send voltage, just for example, turning on this light, it means that it's on. And for on, we can assume it's number 1. That's the binary. When I ask my class what is binary or binary language, they all say binary is ones and zeros. It's a computer language. But what does it mean when we say 1 and 0? Why not 1 and 2? Why not 6 and 7? They are not numbers, they are voltage. So we agreed if there is voltage, we represent it by number 1. If there is no voltage, we represent it by 0. 0 means there is no voltage or off. We exactly have the same things when we go to the networking. It's very important later on when we are talking about the cable length in the networks. We see that this voltage is very, very important. So for example, if I want to show this in a chart, it might be something like this. So imagine here in this chart, I have voltage here and I have time frame here. So imagine voltage is 5 volt. And I want to represent the situation that everything is fine. So it's 0, which is here. And then it goes to 1, which is like this. It's a pattern. So if I translate the good situation off on, it's like this. If I want to represent the bad situation, it's something like this. Off, on, and on again. So this represents the bad situation. And just like that, imagine that your mom and your dad, they are not very angry, but they are not okay as well. Something in the middle. If it's something in the middle, so we can show something like this. Off, on, off, on, off, on. So you turn off the lights and turn it on again 3 times. So it means that it's not too bad, but it's not okay as well. Just like that, we can create so many different scenarios and save it. So imagine that now, if I want to create a table for all different situations, I may have a table like this. This table is so important because later on I go to ASCII website and you see that exactly we do have a table like that. And imagine in this table, we only have 2 columns. In one column, let's just say that I have good situation. It's off and on. We may have the bad situation, off, on, off, on. Normal, 1, 0, 1, 0, 1, just like that. So is it possible to do the same logic to convert everything else, like our numbers, our letters? And the answer is yes. For example, imagine instead of being okay or not okay, is it possible that I represent a number like, or a letter like A, B, hash, question mark? Imagine, for example, I create a table like this and save it in a memory somewhere in a PC. And I say, look, if you get something like this, it means it's letter A. So when you get this voltage, when you get this signal, it means that I mean letter A. And the same things for all other letters, the same things for all other numbers. By doing this way, a PC, a computer, is able to understand what do you mean. In a PC, as discussed, we have hardware and we have software. Imagine that I have this computer, and in the hardware side, I may have a CPU. The CPU is like the brain in our computer. As I said, later on in Certificate 4, we dig more in the hardware sides. We go through all different types of CPUs. We will learn about AMD, Intel, Core i5, Core i7, Core i9, what are the differences between all of the CPU models and etc. But at this stage, to keep it simple, imagine the CPU is the brain of your computer. So what happens if I send, let's just say, this data to CPU, sending 0101010101. The CPU can check. It can go and read the data, this table already saved somewhere in a memory. It can go and read it and check. Let me see. Okay, so you mean letter A. Another signal, another type of pattern of voltage, you mean letter B, you mean letter C. So the CPU fetches all these binary instructions. These numbers 0 and 1, each of this state, we call it a bit. So 0 is a bit, 1 is a bit. Here I have 2 bits, here I have 4 bits. Here I have 6 bits. Later on in our networking unit, we will talk about kilobytes, bytes, megabytes, gigabytes, all of those things. But in a very simple word, gigabyte, it's 1 billion. Gigabyte, it's 1 billion bytes. What is a byte? Anyone knows? A byte is 8 bits. So when you have a block of 8 bits, we call it a byte. And when we say gigabyte, it means 1 million times 8 bits or 8 billion bits. It's a massive number. And it might be interesting for you if I say now all the standard CPUs, they may have a frequency of, let's just say, 2.5 to 3.5 gigahertz, which means a CPU is able to process 2.5 billion bits in a cycle. So it's so fast. Turning on and off a light may take you 1 second or 2 seconds, etc. But this process is so fast. Sending those electric signals or voltage is so fast, and massive number of voltage will send through to the CPU, and the CPU is able to process it. It's able to read it, and based on your commands, if you want to print it, you need to have a printer. It will send a command to the printer and says, look, go and print this symbol, for example, letter A, which represented by this binary number. Or if you connect a display to your computer, again, the CPU will send some commands to the monitor, and the monitor is able to represent your letter, which is connected to those binary values. In this case, that we have 1 and 0, we name it binary. Or computer language, ones and zeros. So now you know what is 1 and 0. 1 means electric pulses or voltage. 0 means there is no voltage or there is no electricity pulse. So that's the binary or computer language that we are able to communicate with the PCs. So you send something like a binary value to this CPU, then the CPU or your PC is connected to a display, and you have letter A saved. Again, it's an agreement. It's an agreement that people, they decided to, for example, represent 010101 to letter A. And then the monitor is able to decode this binary value. And if it's connected to a printer, print it. If it's connected to a monitor, to print, to show you the symbols in a monitor. Okay, so now we all know about what is a bit. Bit is each of those scenarios, having voltage or not having voltage. Byte, it's a block of 8 bits. So if you have a bit like this, or a pattern like this, 1 0 1 1 0 0 1 1, so 1 2 3 4 5 6 7 8, we call this byte, and each of those values are a bit. So when you have like thousands of these bytes, it's kilobyte. When you have a million of bytes, it's megabyte. When you have a billion, it's a gigabyte. Terabytes also the same way. Okay, so Binary also somewhere you can see as a base 2. Base 2 means that we have only two options. Having electricity, not having electricity. Do we have any other third options? No. Your light is, yes, I know that we have lights that are dimmable, that you can put it somewhere in the middle, but imagine, I'm not talking about that area. You can turn on and off a light, or you can turn it off. Even if you dim a light, it's still on. You just reduce the brightness, for example. So we don't have anything in the middle. It's either on or it's off. In binary, there are two options. But for example, in our world, for numbers, we have 0, 1, but we also have 2, 3, 4, up to 9. And all the other numbers are a combination of these 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 digits, but we can make all the other numbers using these 10 digits. But the problem here is for 0 and 1, that's okay. We know that 0 is representing no voltage and 1 showing having voltage. But what about the other numbers? And what about the alphabets? How we are able to convert these values, that we call it decimal. Later on in our networking unit, we go through to this topic. We learn about decimal, we learn about binary, and also we learn about hexadecimal, that we use it nowadays in IP version 6 in our networks. At this stage, we know that we have 10 digits in our daily numbers using numbers. And the problem here is how to convert these other digits, 2, 3, 4, 5, 6, and etc. So the same way, you can imagine that we have a table, and in that table for number 0, we can use this format, showing by 4. Later on in IPv4, you see that we have 8 bits showing numbers. For number 1, I can show it like this. Number 2, I'm able to show it like this. Number 3, it has a logic. I don't want to go to that topic, why we show number 3 like that. Because each of these values had a value. The first from the right, it has a value which is representing by 2 by power of something. I don't want to go to that topic. At this stage, just let to imagine number 3. We can show it that way. Number 4, we can show it like this. Number 4 is 0, 1, 0, 0. Number 5, 0, for example, 1, 0, 1. And the same way for all other numbers. 10, 12, 20, 40, 60, 1,200, any other number. We can represent it like that. So in order to send number 5, we instead send this value to the CPU. For example, in your keyboard, when you type number 5, your CPU converts it to this, and then work on it, and then again it decode it and send the result back to you. So that's fine. For the numbers, we can imagine that we have this format, or we have these values representing those decimal numbers. What about the alphabets? For example, letter A, letter B, letter C, all of those alphabets, how to represent those characters in binary. When I switch back to my computer, I go to ASCII websites, and I show you that even for alphabets, we have a representing number. For example, for letter A, we also have a decimal. So let's say here I have the character. Here I have decimal. Just like here I had decimal. And decimal is our 10-digit numbers, or base 10. Sometimes we name it base 10. Base 10 means using or having 10 digits. Base 2 means only having 2 digits, which is 1 and 0. Base 10 means we have 10 digits, 0, 1 up to 9. So letter A, firstly, it converts to a decimal number like 65. And then in binary, it might be something like this: 0, 1, 1, 2, 3, 4, 5, 6. That's the way that we can represent letter A. So when in your keyboard, you press A, A key, your CPU convert it to this binary value. It understands it as like that. So when you press A in your keyboard, it converts to this binary value. It's just like not sending signal or not sending a voltage, sending voltage. And again, 1, 2, 3, 4, 5. So imagine that your CPU waits for a millisecond. If there is no signal, it assumes that it's zero. If there is no voltage, zero, no voltage, zero, no voltage, zero, just like that. There is a voltage, so it understands this. It sends this pattern. And the same way, for example, for letter B, we represent it by decimal number 66. And it may represent like that. Again, 1, 2, 3, 4, 5, 6. The same for C. It represents by decimal number 67. And it's like this: 1, 2, 3, 4. Awesome. So we can convert all these alphabets. Also for uppercase and lowercase. Example for lowercase a, it has a decimal value which is 97. And it represents like this: 0, 1, 1, 1. Cool. So you see that by using this pattern, and then you can save this table. You can put all of this information in a table, and then the CPU understand. When you press A, it sends that voltage pattern. When you send B or press B, C, A, numbers, symbols also, for example, for a space, for hash, for question mark, for example, for a space has the decimal value of 32, and it shows like this: 0, 0, 1, 1, 2, 3, 4, 5. And that's the same for all other characters. It has an equivalent decimal value, and then there is a logic on how to convert decimal to binary, which is out of the scope of this certificate 3, but later on in certificate 4, we learn how we are able to convert decimal value to binary value. So by doing this, sending electric pulse, a CPU is able to interpret it. This table, we call it ASCII, American Standards to convert this, or to codes and decodes the alphabet symbols to binary value. I go to ASCII websites and I'll show you how it's look like. At this stage, we just wanted to see if we want to communicate with a PC, how we are able to do that, because the PC is not able to understand anything, just voltage or electric pulses. In order to convert our words, numbers, symbols to electric pulses, we need to convert it to binary. In order to do that, we need to have a table or an agreement like this. Then we save all of this information and CPU is able to read it. For example, for a letter like hi in binary, it might be something like this: 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1. So when you type hi in your keyboard, your CPU read with the help of the operating system, it converted to this binary value. And as I mentioned, if you have a printer and you want to print it, exactly it sends these electric pulses to the printer. Printer also is able to understand this. And then it has, for example, letter A symbol connected to this value and it's get printed. ASCII that I will go and have a look on the websites originally had 128 characters. So ASCII handled 128 characters in English. So we do have 28. We have 28 letters and we have 10 numbers. So it's 38 plus uppercase and lowercase and symbols. Having 128 characters was totally fine. But there was a problem. The problem was, what about other languages? Because in this table and in ASCII converts model, there are only 128 characters, which is enough for English letters, digits, and symbols. But what about other languages? For example, what about Chinese, Japanese, Arabic? What about emojis? Now we are using emojis in our phones, in our computers. And also for an emoji, there should be a binary value. For example, when you send one of those emojis, which is smiling or having a sunglass, or all of those emojis, they need to have a binary value. The answer to fix this issue is modern systems called UTF-8. Again, I just want to get you familiar with that. We don't want to go to UTF-8. And it's called Unicoding. And what it does, Unicode, or for example, UTF, is one of the format of Unicoding. It extends the ASCII. ASCII originally handled 128 bits, but using this Unicode, it will extend ASCII to include millions of characters. For example, for this emoji, there might be, for example, a Unicode. The Unicode is, let's say, U plus 1 F603. And again, it has a binary value. The binary value might be something like this: 1 1 1 0 0 0 0 1 1 0 1 0 1 1 0, something like that. So again, when you, for example, send an emoji, firstly it goes and converts to UTF-8, for example, unicoding, and then it goes and converts to binary. Again, the CPU is able to understand. Okay, that's fine. So far, we learned about the binary, what is bit, what is byte, what is ASCII. Before moving to the next step, let's to have a look on ASCII website. So let me reshare my screen and show you ASCII website. ASCII character. Let me reshare my screen. It's on another screen. Screen one. Yeah, I'm sorry. Cool. So ASCII character, as you see, it's an acronym for American Standard Code for Information Interchange. Is a character encoding standard for representing the particular set of 95 printable and 33 control characters, a total of 128 code points. Let's have a look. In the original format of ASCII, it used 7 bits. It's a 7-bit, so now we know what is 7-bit. It means that it can accept electric pulses in a block of 7 bits. 7 bits. Character code where each individual bit represents a unique character. This page shows you the extended ASCII table, which is based on the Windows 1252 character set, which is an 8-bit ASCII table with 256 characters and symbols. It includes all ASCII codes for standard ASCII, and it's a supersets of ISO something in terms of printable characters. So now we know what is ASCII, we know what is 7 bits, 8 bits, and etc. If I go down, now you see here, DEC, it's decimal. So 0, 1, 2, 3, 4, 5, 6, all the numbers you can see up to 31 here, but you can go even further. Hexadecimal, we just skip it. The decimal, we skip it. We don't need it at this stage. Later on, when we go to our networking units, we learn about hexadecimals and etc. Being binary, so you see that 0 represents by 8, 0, 0, 0, 0, 0, 0, 0. It means 0, null character. We name it null. 1 in binary, it represents like 0, 0, 0, 0, 0, 0, 1. 2, it's like 0, 0, 0, 0, 0, 0, 1, 0, and all the way down, you can represent all the numbers like that. In this format that there are only 8 bits, and the lowest number that we may have is 0, 0, 0, 0, 0, and the biggest number that we can have is 1, 1, 1, 1, 1, 1, 1. Correct? Imagine that in our board, if I ask you, what is the biggest 2-digit number? What is the biggest 2-digit number in our own word, in our own word? It's 99. If I ask you what is the biggest 3-digit number, you will say 999. What is the biggest 4-digit number in our word? 9999. Correct. If I ask you what is the lowest 2-digit number in our word, so you will say it's 0. Doesn't matter if it's 4-digit, 3-digit, 5-digit, it's 0. So imagine we are living in a planet that we have only 1 and 0. There is no 2, 3, 4, 5, 6, 7, and 8, and 9. If I ask you what is the biggest 3-digit number in that environment that we have only 1 and 0, the biggest 3-digit number, it's 111, because we have only 1 and 0, and 1 is the biggest number that we have. If I ask you what is the biggest 8-digit number in a binary word, so you will say 81. So here 00000 is the lowest number. Then we have 00001, 10, 11, 100, 101, all the way down. The biggest number that we can make is having 8 ones. And if you convert 8 ones to decimal, it's equal to 255. You can try later if you wish. And if you used IP addressing previously, 255 probably is a familiar number for you. It's a subnet number. Later on, we will learn about it. Anyway, let's go down. As you see, we have 32, 34, all the numbers here. And 255, as you see, it's the biggest number that we can make. And it has all the bits 10 to 1. So 1, 1, 1, 1, 1, 1, 1 is equal to 255. In hexadecimal, we show that with double F. Anyway, so exactly like this, you can go and check other characters. Here, for example, you can go to ASCII characters or ASCII table and see all of those information as well. As you see, for example, characters for Arabic, for Latin, for Thai, for Greek. Let's do, for example, have a look on Arabic. So you see all the Arabic alphabets here. And it has an equivalent. Just like that, and as I show you, again, all of these Unicodes will translate to a binary value, and then the CPU is able to handle it. If I go back and show you, for example, another one like Thai, so you have all of these Thai alphabets and symbols, and you see that they have a Unicode. And again, this Unicode will be converted to binary values, and then the CPU is able to understand it. Okay, so now we are one step closer to talk with our computers. We are able to send a signal or electric pulses. They can use that with transistors and those components. They are able to send voltage to the CPU, and CPU is able to understand it and respond back. So a CPU doesn't have anything, just processing those electric pulses. Cool. So let's go back to my board. Okay, so now we know how to convert our alphabets, letters, and etc., how to convert it to binary and save all of this information in a memory. When you press something in your keyboard or when you touch, for example, an application in your phone, again, the same thing happens. For example, in your phone, when you tap your ANZ Bank icon, it sends a signal, and the signal is all of those binary values, ones and zeros. When you, for example, turn up the volume, when you turn on the volume, when you increase or decrease the brightness, all of those things that you do in your phones or your computers, it needs to eventually turn to binary values. For example, when you're using a stylus pen, again, the display is sensitive, it can detect the pressure, or when you touch, for example, an applications or an icon on your phone, the display is able to feel the pressure, and depending to the amount of pressure or which pixels in your display you touched, it sends a binary command to the CPU, and CPU detect it, process it, and respond back to you. Okay, cool. The next step is now we are able to convert our letters and etc. to binary, but how to talk and communicate with the PC. For example, if I say print hi, it sends a string of ones and zeros as we discussed. It goes to the CPU. But what happens? Nothing. CPU just receives a bunch of bits, bunch of electric signals. So by default, if you send these electric pulses to the CPU, it doesn't do anything. We need to teach the CPU or train the CPU on how to behave if you get, for example, this signal, if you get this pattern of voltage. In order to do that, first of all, we need to use something like a recipe. Let me give you one tangible example. Imagine that we want to make a cake. Okay. So when you want to make a cake, you follow a recipe. The recipe might be in your mind because you did it so many times, you don't need to read it from a recipe or from a book. It's in your mind. But imagine it's a new cake and you have a recipe, you download it from somewhere or it's in a book or magazine, and it has a couple of steps. For example, imagine it says step 1, go and mix, for example, water and I don't know, sugar. Then step 2, for example, add vanilla. Step 3, add eggs. Step 4, all of those steps you can put it here. The only things that you need to do just to follow all of those instructions. And for example here, step 22, put it in oven for 20 minutes. Cool. So you just need to follow all of those instructions and the steps to have a cake. It's the same things when we are working with computer devices. Each of these lines, we name it a code, line of code. Here, in order to make this cake, I have 22 instructions or 22 steps or 22 lines of codes. So let us say we have computer here. Each line is a line of code. If I ask you if the order of these sentences, if the order of these commands are important or not. For example, the first step is to mix water and sugar. Step 2, add vanilla. Step 3, add sugar. Step 22, put it in the oven. Is it okay if I bring this line first? No. So the order is important. Firstly, you need to make this, do that, then do this, then do that, then do that. It's just like, for example, driving a car. When you drive a car, you follow a process. Firstly, for example, you sit in the car, you fasten your seat belt, you turn on the engine, you change. So it has a process, a step by a step. Is it possible that you push the pedal but the engine is still off? No, it doesn't work. So firstly, you need to turn on the engine, then change the gear. Then you are able to push the pedal and then you are able to drive. So it's important to execute all of these step by step. It's very important to do that. This process that we have a bunch of instructions, we call it an algorithm. So here to make a cake, we have an algorithm. So we have an algorithm that we need to follow this algorithm later on. When you are working your assessment task 2, it asks you to write the algorithm for your code. At this stage, we are just mixing the water, blah, 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 blah. It's an algorithm. I can represent it by a flowchart as well. For example, I can say the first step is this. Then, for example, I go to a step 2. Then go to a step 3. And just like that. Sorry, the second one is not in a circle. So you can show it by a flowchart as well. This process we need to follow when we are talking with a computer as well. A step by step, you need to tell the CPU on how to behave. Who performs that task? It's your operating system or OS. For example, if you're using a laptop, it might be Windows, it might be Linux, it might be iOS, it might be Android. So your operating system is responsible to perform all of those tasks. So anyway, each step, we call it a line of code. The whole process, like a recipe, it's an algorithm. So what an algorithm does, it's a step by step process of performing a task. Okay? And then at the end of the task, you will have here your cake, or if it's in a computer, for example, you may have a completed Excel sheet, or it might be a completed Word file, or it might be, for example, processing a PDF file. When you, for example, run a game, when you watch a movie, all of those things, it has an algorithm, a step by a step. If you click here, perform this. If you click there, do that. In a game also, a game might be million lines of code. So for each situation, when you, for example, move your mouse or when you press a key in your keyboard, or for example, when you have a sensor, all of those things will send a signal to your device and the device operating systems. It processes it and handles your commands and instructions. Okay. In order to write these lines of code, there are so many different ways. For example, if I ask you making a cake, Does it have only one recipe? Imagine that you want to make apple cake. Does it have only one recipe? Or no, it might be different recipe with different instructions. The logic is the same. When you want to make a cake, the logic is the same, but the recipe obviously might be different. A person may add sugar a little bit more or a little bit less. Some people, they may add more flavors or so the logic and the process is the same, but there might be different styles. When you go to different restaurants, different chefs, they have their own style. They have their own ingredients. If they make sauce, they have their own secrets. They have their own formula. The process is still the same. For example, when you want to order a dish or a meal in a restaurant, obviously they need to mix some ingredients. They need to cook it for a certain time. The process and the logic is the same, but each chef may have their own style, may have their own flavor, may have their own. It's the same things. When we are writing those lines of codes or how to convert our own language to computer language, there might be different styles. We call that programming language. We call this programming language. There are so many different languages. Which one is better? There is no better one. It's just like if I ask you if Chinese is better or Japanese is better or Korean is better. Different people, they talk different languages. We don't have a better one. They design for different purposes. So the same way that we use different languages in our board, computers also, they are different programming language to convert our intention to some things that a computer is able to follow and process. For example, in computer environments, you may see PHP, JavaScript, Python, C Sharp, C++, and so many. There are so many different programming language. They all design for different purposes. So what they do when we want to communicate with a PC, give it all of those instructions and how to follow, how to proceed, the algorithm, all of those things, they create different types of programming language. The other things that I reckon it's good to mention about the programming language is some programming language are closer to human language. Some of those programming language, they all close to computer or machine language. What does this mean? Which color to choose? Let's choose this color. So programming language levels. We may have machinery language, so they use ones and zeros. And they get binary instructions. We have assembly language, assembly language, like for example, move X or 5 or some things that they use some short instructions, it's better to say, or what we use nowadays, it's high level language. High level language, it means that it's closer to human language. For example, you can say print, for example, print something like hello. So you understand this print hello, the computer also is able to understand. For example, in Python, which is the language, the programming language that we use, it's able to understand this. You just need to type print and the PC is able to understand that. In assembly language, it's a little bit harder because you need to follow some instructions and commands which doesn't have any meaning for you. But that's the way that you can communicate with your PC. You need to memorize it and you need to write it down somewhere like in a cheat sheet. And when you want to communicate with those type of devices, you need to put those commands if you want to, for example, perform a task. Not very close to our human language, but obviously it's not ones and zeros. You don't need to type 101010, which is not practical. The other things that I need to mention, and then after that, I'll go and show you a video. It's for programming language. There are two different types of language. One is compiler based, and the other one is interpreter based. It's very important. Imagine that um, imagine that you want to talk with someone that they are talking another language. For example, you want to talk with a friend or someone, they talk Spanish. So imagine that you have a translator. There are two different scenarios. In the first scenario, you can say something like one sentence. You say it in your own word. Let's say, for example, we speak English. So you say and you tell one sentence in English. Your translator wait for you to finish your sentence. Then they will convert or they will translate it to Spanish. Just like that, you say one sentence, they translate. One sentence, they translate. One sentence, then translate. That's one option. Or sometimes you may, for example, talk about a topic for 2, 3, 4 minutes. And probably you saw all of those translators that are taking notes because they don't want to forget everything. So you talk for 2, 3, 4, 5 minutes. The translator gets all of your talking and then they translate it in one go. Okay, so two options. You can talk something sentence by sentence. You wait for your translator to translate it into another word, into another language. Then you go to the next sentence. Or you can talk for a couple of minutes. Your translator will wait for a few minutes, get all of your talking, and then translate it in one go. If you think about these two scenarios, when you talk sentence by sentence, it's a little bit slower because you need to talk, finish, wait, your translator will translate it, then again he get back to you, you need to talk again, and the process takes a little bit of time. But the good news here is if, for example, you say something that the translator is not 100% sure that if they understood it appropriately or not, they can ask you, sorry, do you mean like this? And you can say yes or no. If it's no, then you can give more information. You can explain it in more detail. So you can be 100% sure the translator understood everything appropriately. If there is any questions or issue or they are not sure if they got what you mean, they have the chance, they have the opportunity to ask you and fix it. In the other side, if you talk for 2, 3, 4 minutes, the translator needs to take some notes. Sometimes they may miss something. Sometimes there might be areas that they're not 100% sure, but because you talked so fast and they didn't have the chance to interrupt you, they may miss something. Misperceptions, misunderstanding, or just forgetting some of your words. But it's much faster. Programming languages also are the same. For example, you may, for example, give instructions to a PC line by line. For example, here that we have the recipe on how to make a cake, you can go and say, look, go and mix water and sugar and blah, blah. Then you wait to see if they are able to do that. Then you go to step 2. Now go and do this. You wait, so they don't. You go to step 3. Or you can just pass the recipe to someone and say, look, this is the recipe and go and do it. If you go a step by step or line by one, it's interpreter based. Line by line. exactly the same way that you have a translator or interpreter. You give the first line, they translate. You give the second one, they translate. You give the third one, they translate. Compiler, as the name explains, it's compile. So you give all the instructions to your programming language, and then they go and execute it in one action, in one go. So compiler are much faster compared to interpreter based, but there is more chance of errors or some things. If you ask which one is better, again, it depends on what do we need. We don't have any better things. It depends on our requirements. Let me firstly show you a video just to change the mode. And then I come back to my board. So let's to have a look on this video, which is talking about the interpreter and compiler based uh, programming language. And then we will be back to my board. Let me switch my screen.
When you land,
Let's just switch the display. So in this video, you can see the difference between interpreter-based programming language and compiler. This is an old video, but it's good to have a look on it.
when you land in the world of computers with their strange, convoluted machine language, it's a bit like landing on another planet whose inhabitants speak an equally strange, convoluted alien language. Getting a mechanic on planet Gobbledygook to repair your spaceship would present the same sort of problem that you have when you want to get a computer to do something. Everything you say has to be translated. And you have a choice between two different sorts of translator. One of them is called an interpreter, and the other is called a compiler. Let's suppose that you've previously written out your list of instructions for the repair of your spaceship. And suppose that you choose the interpreter to do the translating. He reads your first instruction, open lid of rocket engine, translates this into gobbledygook, and immediately passes it on to the mechanic, who executes the instruction. Then the interpreter reads your second instruction, remove spark plug, translates this into gobbledygook, and passes it on to the mechanic, who executes it. And so on and so forth. Now, notice how the interpreter works. He stays with you all the time, and he translates each of your instructions immediately, one by one. This is a rather slow process, because the mechanic has to wait while each instruction is being translated. But, on the other hand, it does give you a chance to correct your mistakes as you go along. If the mechanic removes the wrong spark plug, for instance, you'll see this happen right away, and you'll be able to change your instruction accordingly. Compare this with the way the second sort of translator, the compiler, goes about his work. He takes your complete list of instructions and, without further ado, translates the whole lot straight into gobbledygook. He then hands them back to you and goes away, leaving you all on your own. All this has taken some time, but from now on, things will go very fast. You hand the complete list of gobbledygook to the mechanic, and he executes them all in one go. Bang, bang, bang. There's no waiting about this time. But there's one disadvantage to this, of course. If there was a mistake in your instructions, it's too late now. This analogy comes very close to the way the interpreter and compiler translator programs actually work with computers. An interpreter runs slowly, starts right away, and lets you see how things are going. Whereas a compiler takes extra preparation time before your program can run, but then lets it run very quickly and efficiently. To help you remember the difference between an interpreter and a compiler, look at the words themselves. Inter means between. The interpreter is always between your program and the computer, and it translates line by line. To compile, on the other hand, means to pile together. A compiler piles together your entire program and translates the whole thing all at once. Which one you use on planet Gobbledygook is entirely up to you.
Okay, cool. So this video is so important because when we are using Python, Python is an interpreter-based programming language, and we need to follow its syntax. It means that it goes from the first line of your code, read it, execute it, then it goes to the second line, it goes to the third line, and so on and so forth. So for interpreter-based programming language, we need to always consider this fact that they go from the top to the bottom. It's very important logic. So if you put something in, let's say line 10, and you have something in line 9, whatever you have in line 9 has priority over line 10. It's very important logic because later on, for example, we are working instead for, we are working with IDS systems, firewalls, and IPS systems, and they exactly follow the same logic. For example, you may have some firewall rules to block a traffic. If you put that rule on the top, and then after that you put some other rules that allows the traffic to come through, it doesn't execute it. So it's very important to get the logic. It goes to the first line, then it goes to the second line, then it goes to the third line. In our next few sessions, I give you a couple of examples and practical activities that you see when you put a line of code, let's say in line 20, what might be the difference when you put it in line 15? Sometimes the result is the same, but sometimes it may give you completely different results. So the order of your commands is very important. It's the same thing when you are making a cake. If you don't follow all the recipe, maybe you get something which is pretty similar to a cake, but a highly possible that it doesn't have the same taste. Or sometimes you get something which is not a cake and you will put it in the rubbish. So the order is very important. Let me go back to the board. Okay, cool. So now that you found the difference between the compiler and interpreter, which means that where you can go all the instructions in one go or you can go step by step, it's good to mention that some programming language, they are interpreter based and some of them they are compiler based. For example, uh, let's do choose another color here. Which color? So I can go for pink. And I can give you some examples for each. For example, for interpreter-based programming language, a very good example is Python, which is the programming language that we will have in this current unit. So example of interpreter-based, I can mention Python, JavaScript, Ruby, PHP. PHP, we use it a little bit in Certificate 4 for exposed website vulnerability, Shell, like PowerShell, Bash, and etc., MATLAB. They all are interpreter-based programming language. In the other side, we may have compiler-based like C, like C++, Java. They are compiler-based. Go, Rust. They are programming language that they work as a compiler. They get all the instructions in one go and then they go and execute it. Also, we have something in the middle as well. We have hybrid language. I don't want to go to that topic, but it's good to know that we may have something in the middle. Hybrid language, they have a mix of both approaches. So firstly, they compile into an intermediate format, and then they go and run and execute it or interpret it in a runtime line by line. So firstly, they compile a bunch of instructions, and then they execute it line by line. For example, CNET is one of those examples, or Python compile mode. JavaScript also, it has the modern engine. There might be the hybrid programming language. So now I think that all of us, we have a good understanding of programming language. What is a programming language? If someone asks you what is a programming language, you can say it's a set of rules and symbols that let me write it down. I reckon it's good to write this down just to wrap up the topic of today. So programming language is a set of rules and symbols that help that lets human give instructions to a computer. Okay, so it's a bunch of rules or symbols that allows us to instruct a computer on how to behave. And also, as I mentioned, some of those programming languages are high level, which means that they more close to our daily language, just like go and print. If, for example, when you say if, it's a condition, exactly the same way that say if, for example, if tomorrow is sunny, then do this. If tomorrow is rainy, for example, take an umbrella. Later on, when we are going to conditionals in Python, you see that exactly we use if. So they are high level and they more close to human language. In the other side, we may have some programming language that they are more close to machine language. It's much harder for us because heaps of the commands doesn't make any sense, but they are faster. They're more complex, but they are faster. So each, they have their own advantage and disadvantage. When, for example, you get a programming language closer to human language, it might, for example, sacrifice the speeds a little bit. But when it's closer to the machine, because for each process or for each layer to make it more closer to human language, there should be some extra activities or some extra tasks, which takes time or takes processing power and it makes it a little bit slower. So a programming language you can think as a translator between you and a robot. You say go and execute this, and it goes and perform it. What else? Let's just see what else do we have in our PowerPoint presentation. So now we know about okay, so the next thing that I wanted to mention is a software. What is a software? That was the topic at the beginning of this today's session. Some softwares might be like an operating system, as I mentioned, like Windows or Linux, iOS, Android, and iOS, and etc. Or it might be some third party, let us say. Like, for example, Adobe PDF, Microsoft Office, VLC Player, all of those softwares that they need to be installed on top of an operating system to help you to perform some things. For example, to open a Word file, to open a photo, to play a game, to watch a movie, we need to have some softwares. So if I want to put it in a very simple way, I would say software is a collection of programs that make hardware useful, that make hardware perform a task. So it's a bunch of programs. And the hardware is the physical parts like CPU, disk, keyboard, and etc. And the software is those instructions that tell the hardware on how to behave. And for the last thing today, if I want to categorize those softwares, I can say there are different types of software. So with the help of programming language, we can create softwares. For example, Microsoft Office, it might be written by C Sharp. Another software, it might be written by Python. A website, for example, it's a type of software. A browser, it might be a software. The application that you have in your phones, they all written with one of these programming language. For example, Python, you may use it for example, website, databases, and etc. Each programming language, it has its own advantage and disadvantage. For example, a programming language might be the best option to, for example, create databases. Another programming language might be the best option, for example, to create a web browser. So all of those programming language, they can be used to create different types of softwares. Types of useful softwares that we now use in our daily life. It might be written in Python, or it might be written in C Sharp or C++. And type of software, we have system software. So we have system software. What they do, they run and manage the computer hardware like Windows, macOS, Linux, Android device drivers. We call it system software. So they run and manage the computer hardware. We have application software. Application software, they help you to perform different tasks like Microsoft Word, Excel, Chrome, Safari, Photoshop, VLC player. All of those softwares are application softwares. Usually you need to have an operating system or a system software to install application software and use them. We also have programming software. Programming, I need double M. Programming software they use to write other software like VS Code. So next session I will talk about IDEs to see how they can help us to have a better experience when we want to write codes. VS Code is an example, PyCharm. I'll show you visual VS Codes and PyCharm in our tomorrow session. Eclipse, compilers, interpreters, they all are programming softwares. And eventually we have embedded software built into device, built into devices. For example, like ECU that you have in your car, the computer in your car. Your car has a computer which handles so many things. For example, car ECU, like for example, in your washing machine, in your refrigerator, in your aircon, they also have some type of software. For example, in your refrigerator, it has a software, it checks the temperature, and it can turn on and off the engine. In your washing machine also. It gets different um, commands, for example, water temperature, all of those things. They already come with those softwares or firmwares. All of your devices, even like your aircon, they come with those type of softwares. We call them embedded software or built into device softwares, and they all perform the same task. They get some instructions. For example, in your aircon, when you change to heating or cooling, you change the temperature, it gets all of those commands, it changes it to binary, send it to a CPU, the CPU will perform all of those things. And then, for example, if the temperature is, let's say, over 20, it can send a command, turn the engine on or turn the motor on, and, for example, cool your room. All good. So that's all about our tonight session, talking about the binary programming language, high level, low level, talking about softwares, talking about algorithms. So we had heaps of contents in our tonight session. I hope that you enjoyed. Let me see what you put down in the chat.